Alrighty. So I've been trying to get a bunch of grading done, actually for a different course that was way behind on grading, and so I kind of lost track of all this stuff for the moment, and looked back and noticed that I should have opened up Module 5 like Sunday night or yesterday morning, something like that. So I just opened it up. I don't think I've ever made a Module 4 quiz, have I? No, okay. So we'll have to look at getting the quiz done somehow or other. But so I opened up Module 5 so you can get started on it. I kind of got more caught up with the grading there. I need to do grading for you all too, but I'll also try to get caught up on Module 5 here. So get the due dates actually to be correct, and I think take out these links. I'm pretty sure those links, I had to start taking out those links because they weren't actually linked to what they ought to be linked to. Like if I click that, I think it goes to instructional content, but if you actually look at the course name or number and all that, it says CT Math 24. That's not our section. Okay, so what happened was when this stuff got copied from the original, it did not, the links didn't update to the local section, and so those links are no good. I'll get those out of there so they aren't a problem, and fix all the little things. I just hadn't gotten to that, like the project is 50 points, it's not 40 points, and that kind of thing. Let's see. So at any rate, that's open. I don't think there's anything under instructional content right now. Again, I'll get going on that, and we'll talk about some things today. There is the discussion, though. You can get working on that. The due dates just say things like Thursdays and Sundays and so forth, so I'll have to fix those up. Well, the Sunday's fine. It's just not this Sunday. It's a week from Sunday. And this, I believe, the presentation part, that's all fine. It just needs the due date fixed up to be specific to this semester. And guided project, there's some resources there, but the actual project you can't see at this moment. But again, so in the next couple of days, hopefully I'll get that stuff taken care of, and also get some more grading done for this course. So let's see. So with that, we're moving into Chapter 4. Do y'all have any questions over Chapter 3 at this point? Anything with the chi-squared you're wondering about? Okay, so let's look, the text. So the big ideas in the text. So in Chapter 4, let me just go here. It's still kind of big, isn't it? Huh, it's kind of weird. Huh. Oh, I see. It's the window is What happens if you do that? There we go. That looks a little better. There. Okay, so as we move into chapter 4, again, we're asking the same sorts of questions. Okay, so let me get this out. Let's remember to switch to this view. Okay. So in chapter 3, what we did there, our data consisted of counting things, right? And so what we would tend to do was we might get something like a p hat. So our data produced p hat. Okay, and p hat was the number of successes divided by the number of observations or trials, something like that. Okay? Now, the number of successes was just a sum of ones, right? We said, oh, we'll call it a 1 if it's a success, if it's whatever outcome we're looking for, and we'll call it a 0 otherwise. That's kind of how we ended up getting our number of successes, right? So as you look at that, that would look something like, 1 plus 0 plus 1 plus 1 plus 0 plus, something like that, plus 1, all divided by n, where n was our number of observations. Okay, so that was kind of our data. And then even when we went to the whole two-variable idea and so forth, we're still counting number of successes and number of observations total. Even when we do that chi-square and we fill stuff in, that's what we get is this kind of idea. Okay, everybody good with that? Any question that that's what we were doing? No. Okay. So in chapter 4, okay, what we do is in this case, the thing we're going to focus on is our data are going to produce a sample mean, x bar, sample mean. And so that will be, now, I'm not doing this part, I'm really just going straight to there. It's observation 1 plus observation 2 plus observation 3 plus observation n divided by n. Okay, now when you look at it this way, are you starting to believe me that a proportion is really just an average? Right? I mean, they're the same thing. I could have written here, right, like, I don't know if I'd use outcome or something like that, but outcome 1, outcome 2, outcome 3, right? And they're, in this case, though, they're either a value of 1 or 0. Here, they're a continuum. We can have all sorts of values here. These are real numbers. And so that's the big difference, is that as we go to chapter 4, we're going to get numerical data. And with numerical data, we can do things like take means. Okay, so the mean is going to be kind of the main thing as opposed to the proportion being the main thing. Okay? But in some ways, I mean, the calculations, of course, are totally different because, well, we're dealing with real numbers instead of these categorical things where we're counting them. Okay, but in the end, right, we're really just going to do the same sort of thing. Okay, so another comparison. So we have this, right? Just proportion versus a mean. But really, a proportion is a mean. Okay, they're really just the same thing. Okay, so now, when we start looking at these variables, again, comparing Chapter 3 with Chapter 4, and the reason I'm doing this is my hope is by the end of the semester, you really will get the idea that we spent most of the semester just solving the same problem over and over again. Okay, and if you begin to see it that way, that takes a lot of the mystery out of all the stat vocabulary that people like to throw around. Okay, you find somebody who knows their statistics, they're usually going to be real big on just throwing the vocabulary around. Okay, but if you get the idea of what a hypothesis test, mostly we're looking at between two variables, but we'll add more variables right at the end of the semester. If you get what that idea is and realize that all these tests are just asking that same question, but for different types of data, different situations, then it really empowers you to get what's going on with the statistics. Okay, you don't need to know all the little calculations and all that kind of stuff. You need to know what it's trying to do. Okay, because the technology will do all the little calculations for you, and it'll do it for the totally wrong thing if you ask it to. Okay, so you want to ask it to do it for the right thing, the right stuff. Okay, so again, Chapter 3 with our two variables. What we ended up with was that if we say, now, again, with count data, it really doesn't matter where you put things, but let's say up here was our explanatory variable. Okay, and so our explanatory variable, right, that had, I'll call them C's for column, but I'm also going to say category, so it'll seem like maybe I'm using a C for category, but I'm actually using the C for column. So, we had column 1, column 2, we could have gone up to any number of columns, maybe. I don't think we ever did anything more than about 4 columns, but maybe 5. But, we had these columns. That was our explanatory variable. And then, over here, we have our response variable. And for the response variable, there were different categories, but I'm going to call those R's for row. So we had row 1, row 2, and down to some row M. Okay, and we filled that thing in. Well, I didn't do a very good job there. C2. There we go. And those are dots and so forth. But we filled those in with data. And that's how we took our data, and then we calculated something from that. Okay. In Chapter 4, the difference will be that our explanatory variable is actually the same. It is still going to be categorical. So I'm still going to have a column 1, a column 2. This is probably how you would see your data. Now, certainly somebody could write the data horizontally instead of vertically. But typically, when you look at a data set, you're going to see column headers like this, and then data down, that sort of thing. And then the response okay, the response is going to be numerical. And so here, what you're going to see is something like an X, and I'm going to use a double subscript. That might be scary to you, but the first one is for column 1. Okay, and then I'll have a 1 here for the first row. You know, and then an X12 and an X13, and then here I could have an X21, an X22, X23, X24, and and so forth. XN1, XN2, way down here to maybe some XNM, wherever it stops. The columns don't have to have the same number of data in them. Okay, so what's changed is just that in Chapter 3, we had explanatory variable was categorical, and so we had columns for each category. But then the response variable was categorical, and so we just could count up the numbers in each one of these. But now in Chapter 4, that response variable is numerical, so it will be a whole continuum. And we could turn this into that simply by bracketing things. Suppose these are, I don't know, first thing that comes to mind is paddle lengths. You're going, what? Paddle lengths? Well, so I canoe a lot. Well, I don't know, probably more than you. How about that? I've made paddles and different lengths. So like I've made one as tall as this for a stand-up paddleboard, that kind of thing. And so I could make all these different paddle lengths and sort of ask, well, which one works best under what conditions or something like that. But these could all be paddle lengths, which would be a continuum, because I can make them any length I want. But I could also categorize them into like short, medium, long. Something like that. Or sit down, high kneel, stand up. Okay, so I could categorize them. They'd be different lengths, but I could categorize them and put them into a format like this. Okay, so numerical data I can very easily turn into count data simply by creating bins for my different numbers. Okay, and just counting how many are in each bin. All right, so that's the difference when we go to two variables. But because our data now looks like this, we need a new way to analyze it. We need a new way to come up with a p-value. Now, and back here, for our chi-square test, right, H0, the null hypothesis, right, that was that, let's do it this way so we can match up here. All these columns had the same relative proportions. That was H0. And then our p-value was, well, okay, they probably don't actually have the same relative proportions. How likely is it that I could get these deviations of proportions? How likely could I get these different proportions if all these data actually did come from something where the columns were all the same, proportion-wise, okay, relative proportions, right? You know, this was a half, and that was a third, and that was an eighth or something, and whatever it works out to be to make that work. Okay, and that was a half and a fourth or a third or whatever I said, and an eighth, and right, that these were all the same proportions, relative proportions. That's H0. Okay? It's probably worth writing down under this thing, right? H0, all, and I'm going to use columns because that is in columns over there in chapter 4. So all columns have same relative proportions. Okay, and then we calculated a p-value based on that hypothesis. Right? We created a table that this was true, and we looked at the difference between those tables, and we had to, you know, do a little calculation to come up with our chi-square statistic. But that's what we did. Now here, our H0 is that all columns have the same mean. And if you think about it a little bit, if these all had the same mean, and I broke them up into sections and counted how many things were in each section and so forth, the proportions would probably have to be about the same. I've never had anybody do that exercise, but that might not be a bad exercise to do, is you know, take something here where all the columns have the same mean, and then count, you know, how many items are in each bin of something, and you know, and then look at it as a table this way, and you'll see, you know, most likely the proportions should be about the same. Now, although when you do that, you do lose some information. Okay, because here I have all the values, the actual values. If I start sorting them into bins, and I just tell you, oh, I'm going to give you a short paddle. Well, how short? I mean, is it really, really short, or just barely in the short category? Well, I don't know. I'm not going to tell you. It's just short. Okay, so you've lost some information compared to the items here. Okay. But, you know, as you look at this, the null hypotheses are essentially the same. Now, again, another way to talk about the null hypothesis under either of these is the null hypothesis is the two variables here, the explanatory and the response variable, are independent. Okay, that's another way to say this same thing. They're independent. Okay, because if all the columns have the same relative proportions, then knowing I'm in any one of these columns won't change my prediction as to what row I might be in. Okay, and well, if I don't change my prediction, they're independent. I haven't gained any information. So the same thing here is if these means in each of these are all the same, then whatever this response variable is independent of whatever that explanatory variable is. Now actually the typical thing I use for this, we're in a farming area, we're in a rural agricultural area. So imagine that the different columns are different types of fertilizer. Okay, you need to fertilize your soybeans or your corn. That's pretty much all you see around here, corn and soybeans. You want to fertilize one of those, and you want to check, well, which one has the highest yield? And so what I could do is perform an experiment where I try different fertilizers in all different places in some fields, right? Randomly pick spots in the field and use different fertilizers. And then in each of those spots, check the yield. Right? So the fertilizer is categorical. Right? It might be, the case of no fertilizer. Right? That's always good. No treatment. And then maybe a high phosphorus fertilizer, a high nitrogen fertilizer, something like that. And I could try those different fertilizers out. And then, so those are categories. But then I could check the yield, something like bushels per acre, but that's numerical, bushels per acre. And I would get data like this, and the question is, well, did it matter? Could I predict, would I change my prediction on my bushels per acre if I knew which fertilizer you used? Right? And if I do, if I change my prediction on bushels per acre based on the fertilizer, then they're dependent. Okay? Because I change my prediction depending on which one of those we pick. Okay? If they're all the same average, then I guess it doesn't matter what fertilizer I used. You get the same bushels per acre no matter what. They're independent. Doesn't matter. Okay, so in chapter 4, ultimately we want to be able to get a p-value for that situation. We want to get our data in columns for a categorical explanatory variable. We'll look at the means. Do a little more than that, but we'll look at the means, and we will try to determine whether or not we think all the columns probably do have the same mean. Now, in the end, we don't know. Again, we just fail to reject this. So if they're close enough, then we'll stick with our null hypothesis. But if we get a really small p-value, okay, and again, the p-value is just what's the probability of getting these data if this is really true? And if it's a really small p-value, like 0.01 or something, we'll say, oh, yeah, these data probably did not come from something like this, where all the columns had the same mean. Something else was going on. And so we'll end up going with our alternate hypothesis. Okay, so ultimately this is our problem. And you see, it really is pretty much the same problem we had here. Okay, we really haven't changed. The only thing we've really changed is what our data look like. How do we get our data? How do they come? Do they come as all count data, all categorical variables? Or are they mixed this way in that the explanatory is categorical and the response is numerical? If that's the case, we use Chapter 4 stuff. Okay, and kind of finally on this problem, we can look at it graphically now. So with count data, you really can't look at it graphically so much. You really just have to look at the tables, the contingency tables we had. But now, graphically, what we can do is, here's our category 1, category 2, category 3, and category 4. Say we've got 4 categories. We can take that numerical data, and we learned about box plots, right? The 5-number summary plots. And, so if I have a box plot like that, and these data under C2, look like that, C3, their box plot looks like that, and then C4, we get something like that. Well, that's a lot like for 2 numerical variables, we get to do a scatter plot. In this case, we can do a plot like this. You could just do what they call a dot plot. So instead of showing the maximum, the minimum, the median, and the 2 quartiles, you could just plot all the points numerically. And get a bunch of dots, but this is a little better, I think. You see a little more with this. So as you look at that, though, depending on the scale and so forth, but if we assume, this started at 0 and it's a normal sort of scale, nothing weird going on with the scale, I might look at that and say, oh, I don't think they probably have the same mean. All right? I can look at that and kind of go, I'll be surprised if I get a large p-value. Okay, I might. I have to calculate it to know, but but we can do this with our data. Okay, we can create some box plots and just kind of look at it graphically and get an intuitive notion as to whether or not we think something's going on. Okay, and as I look at these data, I'd probably think somehow the different columns are different. Okay? I might be wrong. Well, they're obviously different, but are they statistically different? Is there enough evidence to claim they are statistically different? Don't know. I would have to do the statistics to find out. Does that make sense? Any questions about a graph like that? And just that can help us answer our question. Okay, my question really comes down to, are these columns basically all the same, or are they different somehow? At least one of them. Is at least one of them different? And, well, I can look at that and go, I think at least one's different. Okay? But again, that's not good enough. We need to do our statistical analysis, get a p-value, and look at that p-value so that everybody has the same yardstick. Okay, because see, I could look at this and say, yeah, I think they look different, but somebody else could look at it and say, no, I think they look pretty much the same. Who am I to argue, right? You know, whereas if we use our p-value in the statistical analysis, at least everybody can agree that's the p-value. They still may not want to change their mind. All you have to do is look at all the political stuff out there. Data does not seem to change many people's minds. It's amazing to me as a person who teaches statistics. But, you know, you can't argue with the data. I mean, you can ignore the data, but you can't argue with the data. Okay? So, yes, sir?
On the other side of that coin, could you say that data is being manipulated to point out a certain point of view if you're trying to use
Well, I mean, you can always leave out data,
yeah.
but then that's not really the data.
Okay.
You know, that, I mean, so now you're lying.
Yeah.
Okay, so if you're lying, well, that's not, well, it's data in the sense that, oh,
But it's
if I can catch you lying, then I know there's a data point that says you lie,
Okay.
and I'm not going to believe you the next time you try to give me data, right? But yeah, if you withhold data and nobody knows,
Then you're just using.
then you're still lying, but nobody would know you're lying, you know. And so in that way, again, if everybody thinks that data is correct,
That's
they can't argue with the data,
Yeah.
right? You know, and so there's always the human element in data that, yeah, if I only, you know, if I take 1 million data points and decide that, oh, these 300,000 data points tell my story, and I leave out the other ones, well, you know, if nobody catches me,
That's like,
then I've just, you know,
so like taking a
put one over on everybody,
So like
right?
taking a survey out of 100 people and
Yeah, but only reporting the 20 that
Yeah.
tell your story. But then, of course, you're not using science. You're basically, you never needed to take the survey to begin with,
yeah.
right? Because you know the answer you want to tell somebody. So at that point, you know, again, if somebody's really out to hide it from you, yeah, you wouldn't know. There is that human element. There's always that human element. But if we can assume that, you know, people are not out to do that. However, along those lines, actually, that brings up an interesting thing. A few years back, one of the California schools, California Davis or Stanford or somebody, tried to repeat, I think it was about 300 social experiments that were in the literature, and it found a p-value less than 0.05, you know, so, and they tried to repeat those experiments, and only a very few had a small p-value again when they tried to reproduce those experiments. And so actually that can also happen with data, is remember, rare things do happen. I mean, that's the definition of rare. If it's rare, then it can happen. Okay? So if it's rare, it can happen and will. Not real often. Again, definition of rare. But if you think of, say, 1,000 people all do the same study, and whatever they're studying shouldn't pass the p-value test. Okay, because really underlying there's nothing going on. Well, let's, instead of 1,000, let's go with 100. If 100 people all do the same study, then actually alpha equal 05 says, by definition, we would expect 5 of those studies to be significant, to show a significant difference, even though there is none. Okay? So, if you get enough people studying the same thing, you will get a significant answer. You maybe shouldn't, but you will. Okay? Again, rare events happen, and if all you need is 1 out of 20, you don't need that many experiments to have, to go to get this possible outcome. Okay, so back to this stuff. So we want to look at that. It starts with just the single variable stuff again. Okay, so chapter 4 begins with just a basic hypothesis test of you gather data and you want to know is mu equal to some mu 0 or is it not? Okay, so that's for one set of data, you're just asking that question. Actually, even more likely, what you would ask about is a confidence interval. On your sample mean. Okay, and this confidence interval is the same confidence interval we had before. You're going to have your x bar, so that's your data point. You take a bunch of data, you find the sample mean, you get x bar, and then that's plus or minus your number of standard deviations times your standard error for that data set. Okay, so here this will be your z alpha over 2. Okay, it's your number of standard deviations stuff. And then times your standard error. And that's what we did for proportions back in chapter 3. I mean, the confidence intervals on the mean are always the same thing. Now, where this chapter changes a little bit, though, is now with proportions, we sort of worried about this. So remember in chapter 3 again, we needed n times p and n times 1 minus p. We wanted those bigger than, anybody remember when I shouted out? What do we want those bigger than? Well, I'll take 5 while I'm waiting to hear the answer. That help?
Greater than 5.
5, thank you. How'd you ever know? Right? So, right, this needed to be greater than 5. Well, that's, in this case, that's both talking about P and N. Okay? In chapter 4, well, for Z alpha over 2, okay, we want N to be greater than 30, say. Okay, the problem is statistically, even though even if X is coming from a normal distribution and all that kind of stuff, if we take a small sample and we look at its mean, it actually ends up kind of varying more than we would expect. Okay, so if n is less than 30, now actually, well, we put less than or equal to 30, right at 30, who really cares? I mean, it's somewhere around 30. If n is less than or equal to 30, we're going to say use t, but actually there's no reason why you can't use t even when n is greater than 30. So we'll look at what t is doing for us. But we use x bar plus or minus t alpha over 2, and then I'm going to put n minus 1 because there's a degrees of freedom thing there, times the standard error. So, okay, in chapter 3, they didn't really give us a method to work with this stuff if this number was too small. They just said, well, it really ought to be 5 or more. Okay, but in chapter 4, if our n is too small to use the normal distribution, they give us an alternative. And so they talk about it here in the one sample means with a t distribution. And if we look down here, we see a normal probability table, and then we see the t distribution table. And notice the picture of the t distribution. It looks like a normal distribution. Okay, the only difference is that, again, for small samples, they've realized that things vary more. It's a flatter distribution. And so what you have is, if this is the normal distribution here, what happens is you get things like this. So this is a t distribution with small n, and this is a t distribution with maybe a medium n, okay, sample size. And as you have a bigger and bigger sample, the t distribution, that's the degrees of freedom here, the t distribution looks more and more and more like a normal distribution. Okay, it just gets more peaked and a little narrower. But that's the only difference that's going on. So, though, if you start looking at numbers of standard deviations, then you get bigger probabilities for the same standard deviation. And if we look here, so the way one reads this is, for instance, if we wanted a 95% confidence interval, we would look at this table where it says 2 tails and 0.05, because if it's a 95% confidence interval, right, that's really talking about alpha. Alpha is 0.05. And it's two-sided, that's the two-tail part. Then for the different numbers of degrees of freedom, so degrees of freedom of 1, 2, and so forth, then the number you see under there is this t alpha over 2 n minus 1. Okay, that's that number of standard deviations you need. So notice, degrees of freedom of 1, that means I had 2 data points. Then if I try to create a confidence interval with 2 data points, it says I need to use 12.71 standard deviations. That's a lot of standard deviations. Okay, but if you look down here, notice, remember that for the normal distribution, that number of standard deviations is 1.96. And that's exactly what that goes to. And that's what the infinity sign there is if you have, you know, an infinite sample. I guess you're looking at an infinite population. Well, in that case, yeah, it's the normal distribution. Okay, so if you look at those numbers, they get closer and closer and closer to that 1.96. Now, here's 30. 30 instead of 1.96 should be 2.04. Who cares? It's all, we don't know the right answer anyway, right? It's around 2. That's what we've been saying. It's about 2 standard deviations. Well, so pretty much statisticians say, yeah, you hit a sample size of 30, just assume a z distribution or a standard normal kind of thing. And so that's what's going on, though, with the t distribution. It is just really there for these smaller samples. You know, when you get up here, if I just have a sample size of 10, then it says about 2.26. Well, I mean, when you think about that, that's what, like 12.5% bigger, right? Compared to 2. 2.26 is like 12.5% bigger. So that's a lot bigger. I mean, when you start thinking about it that way, the confidence interval and also then hypothesis tests and so forth are, you know, it starts to matter at that point. And so when you have small samples, you want to remember the t-value thing. Okay? And homework exercises, that kind of thing, will give you a chance to do that. And and we're way out of time, so sorry about that. And I will see you next week, but I'll be getting stuff on the web to help you out.